Right, next lesson on limits, and this is using analytical methods for finding limits. So sometimes we need to definitely use algebra ways to do it, partly because we don't always have a graph, and then sometimes when you look at the graph you can't see everything. So things like holes in the graph and stuff you don't actually see, and just different things that can be misleading. But we also don't have the graph always, so these are different things that we might do. Some of these we're not going to do, or we're going to do lightly because there's other things that we can do, but we're going to go through a lot of these methods because we're going to learn a better way to do it later. All right, so substitution. So the very first thing that you will always do is you will just do direct substitution first. So if you have a polynomial or a rational function, which is a polynomial over a polynomial, then this is a theorem that says that the limit is in fact the value when you plug the number in. Like x is approaching c, the answer for the limit is f of c, providing you don't get denominator equal to 0. But we're going to learn some ways to handle if you get weird stuff that doesn't work. Now that's also going to be true for almost any other type of function. As long as it's continuous, you plug in, you get an answer, that's pretty much going to be your limit. So that's really going to be the first step always. So for these two examples, we're going to just do direct substitution. So on this first example, I have the limit as x approaches 2, and so I'm just going to plug in 2. So I'm going to write out lots of steps here, but that's not what you're going to do later. Of course, you'll just do the arithmetic. Now, I will say it's generally better to write it out than it is to try to do all of it in your head, because you tend to make mistakes if you do all of it in your head. But at this point, now I can see it, so it's easier. I can see the first is 12, because I have 2 squared is 4, times 3 is 12, minus 10 plus 4, so that's going to be 6. On B, I'm going to do direct substitution, so I'm going to get, now this time I'm not going to write 2 cubed, I'm just going to say, oh, that's 8 plus 1 over 2 plus 1, that's 9 over 3, which is 3. So again, sometimes, even when it's simple arithmetic, it's better to write a little bit of it down and go ahead and when you're substituting instead of trying to do all of it in your head. So let's do direct substitution again. So I have ln of e over 3e. Well, ln of e is one of those log properties, and log properties are super important in calculus. We're going to use them all the time. So ln of e is one of those you should know as being 1. So we get 1 over 3e, and that's just the answer. So you don't stress over simplifying. I mean, that is simplified, so that's just the answer. Okay, so here we're going to have third root of 4 plus 4. That's third root of 8, and so that's going to be 2, because 2 times 2 times 2 is 8. All right, so here we have a limit for a trig function. So we have the limit, sorry, I don't need to keep writing limit, I'm going to plug it in. So I'm going to have sine of 2 times pi over 6, which is going to be sine of pi over 3. And then sine of pi over 3 is one of those that you should know. You need to know your unit circle, square root of 3 over 2. So unit circle, another thing that's going to be used a lot in calculus. Also notice my equal signs all nice and lined up on the left here. That makes my work just follow. You really, really, really need to get in the habit of writing things clearly, because once we get into calculus further, it's going to just be super important to be able to express things properly. So it's really important to write things carefully, and no better time to practice than now. So I'm going to plug in here. So I plug in the 5. So I get log base 3 of 9. So again, log properties. So this is 3 raised to what is 9, and that answer is 2. So the answer for that log is 2. So if you struggled a bit on those problems with the log properties or even the unit circle, just think about those are things that you should review a lot and you should go over. All right, so one algebraic method that we can do is we can talk about what to do for discontinuities. So basically, if you have a rational function and you wanted to find the discontinuities, one step you would do is you would try to factor, and that's numerator and denominator. And that's how you would sort of see your discontinuities. Now, the careful thing that we have to be really careful about is if you choose to simplify. So a lot of people would just say, well, you just simplify there and you cross it off. Well, that's what we do in Algebra 2 because we are trying to just practice the processes, but here we have to be careful about simplifying. So you're going to simplify, but you have to use caution there. You cannot just cross factors off and say they just don't exist. You have to talk about that. So we'll see that in some examples. And then basically you have a point discontinuity. In other words, you have a hole. This is for rational functions, so polynomial over polynomial. You have a point discontinuity when you have not a 0, and I'm not going to write it that way. You have 0 over 0, okay? So that means that the reason it was a point discontinuity is you can basically cross those off, but again, we use caution there. And then you would have a non-removable, and this one would be removable, is what we call it, because it's just a hole, so this is removable. And then we would have a non-removable, oh, just realized I didn't spell that right. We have a non-removable discontinuity when you have non-zero over 0. Okay, and that would be a non-removable discontinuity. So generally an asymptote, vertical asymptote. So basically what we're going to do, here's the difference, okay? So this is where we have to be really careful. If I want to do this limit, the very first thing I would try is plugging in 2. Well, when I plug 2 in, on the top I'm going to get 4 plus 2 minus 6, which is 0. And on the bottom I'm going to get 4 minus 12, which is negative 8 plus 8, which is 0. So I get 0 over 0. One thing to never, ever, 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 ever write is that this equals 0 over 0. That's bad. Never write that, okay? Never. That's because you can't equal that. That's an indeterminate thing, so never, ever, ever write that, okay? So really important to remember that. Never write that, okay? So from the beginning, right now, we're not going to do that. So I notice that that's what I get. So I'm just going to go ahead and realize, okay, I'm going to factor this. So I'm going to factor the top and factor the bottom. Factoring is another thing that it's really important that you know how to do quickly. So if you don't know how to factor, do logs, or your unit circle, those are all 3 things that you need to independently practice. You cannot afford to be factoring by trying to do a whole bunch of long, complicated stuff. You should know immediately that those are the factors, and this one should be immediately obvious also. If it's not, that means you need to practice and learn about factoring. Now, in Algebra 2, you would have just said, oh, you know what, we're just going to cross those off, okay? Problem is, we can't cross those off and say these are still equal in general. Now, I can do it here. So here, this equal sign is absolutely okay because the limits are equal. So let's talk a minute about why these 2 functions are different. So this function and this function, okay? If you were to graph them on the calculator, they would look the same because you wouldn't see the difference in them. They would look exactly identical unless you traced. And when you traced and you got near the point x equals 2 and you hit x equals 2, it's going to tell you undefined because there's a hole in the graph for this one up here. This one has a hole. The bottom one does not have a hole. That's the only difference in these 2 graphs, okay? Well, what's important about that is the hole is at 2. Well, 2 is where I want the limit. So handy for me, their limits are the same. This one has a hole, no hole. That's the only difference in the two graphs. So the limits are exactly the same when I'm going to 2. I don't get any difference when x goes to 2. They both have the same answer. The advantage to this bottom one, that's why the limits can be equal, okay? The functions are not equal, but the limits are. But if I plug 2 in now, since this graph has no hole in it, I can find the value that is in the hole of the original graph. So now I plug in 2, I get 2 plus 3 over 2 minus 4, which is going to be negative 5 over 2. So now I did get an answer for the limit, okay? So factoring and canceling is acceptable for you to write an equal sign here because the limits are equal. This is not acceptable. Okay, so I'm going to put a big X through this after I'm done. This is not a true statement. Okay, this is not true. Okay, that is definitely not true. So do not ever write that. It is not true. Okay, you did it a lot in Algebra 2 because we just sort of ignored the fact that here's how I can make it true, comma, x not equal to 2. Now it's true. Okay, so now you're okay as long as you put x not equal to 2. All right, but it's not true without that because they're only the same everywhere except at 2. This left one has a hole, no hole. Okay, so they are not equal, so no equal sign can go there. But equals can go here for limits because their limits are the same. So that's the first sort of abstract thing you need to start thinking about. So if we were to look at the graph, and here's the graph. Now, if you look at it on the calculator, you wouldn't see this hole, right? This would just be smoothed over. You wouldn't even know there was a hole there. That's the reason, again, we have to know more than the calculator, okay? So if I look at the limit as x approaches 2, we just found it, it was negative 5/2. And again, looking at the graph, I can't tell that's exactly negative 5/2, right? That's why we need an algebraic method. Now let's look at the limits as I approach 4 from the right. So this one says limit as x approaches 4 from the right. So if I'm going to be on the right of 4, that means I'm following the graph this way. Well, what's the graph doing? Well, it's going to infinity, so that side is infinity. This one says take the limit as x approaches 4 from the left. So now I'm on the left side of 4, I'm approaching, and my answer is going to be minus infinity, okay? And if you remember from pre-calc, or maybe even Algebra 2, but definitely pre-calc, if you are approaching a number on a rational function and you get infinity or minus infinity or on either side of it, it tells you there's an asymptote, okay? And so, or vice versa. If you know there's a vertical asymptote, then you know that would happen. Okay, so now let's figure out what happens. So right now, until we learn something later in the course, right now if you get 0 over 0, you're going to try to do algebra to get the discontinuity removed, okay? If it doesn't do that, then you're not going to be able to answer it now in certain cases, okay? Now, when we do the limits that I did about 4, well, looking at the graph, it was really easy to see it was positive or negative infinity. Well, what makes it easier here is once I factored this, so remember these factors were x, the top was x plus 3 times x minus 2, and the bottom was x minus 4 times x minus 2. So those were the factors that we already had. So we know that 2 was a whole because you had a factor in the top and bottom that were the same. You know that at 4 you have a vertical asymptote because the top is not 0 when you plug in 4 and the bottom is 0. So if we already know that we're supposed to be getting infinity, okay, and we know that this is the same as the limit as x approaches 4 from the right of x plus 3 over x minus 4. Again, the limits are equal. The functions are not, but the limits are. Well, we know there's an asymptote there. So we know that it has to be infinity or minus infinity. Because for rational functions, a vertical asymptote is like a brick wall. The function is going to be going towards that wall and it can't hit it, but the function can't stop either. So it has to turn up or it has to turn down. It doesn't have any choice. So all I need to do to figure out whether it's positive or negative infinity is pick a number really close to 4, but to the right of 4, and see if I get positive numbers or negative numbers. That's the easiest way to figure it out. So a number close to 4, so use, say, 4.1. Okay, we're going to plug 4.1 in, and we're going to see what happens. Well, you would have 4.1 plus 3 over 4.1 minus 4. Now, I don't need to figure that answer out. I just know that it's positive and positive, which means this is positive, which means this side is going to positive infinity. Okay, because I know that it's going to negative infinity or positive infinity, one of the two, because I know there's a vertical asymptote there. So we can do the exact same thing from the other side, but when we're on the other side, we're approaching from the left. So let's say use 3.9. So now I would have 3.9 plus 3 over 3.9 minus 4. Again, I don't care what answer I get, just the sign of it. That's positive, that's negative. So that's going to be overall a negative number, which means I'm going to minus infinity. Okay? So the one thing you'll notice about calculus is there's a lot of stuff we need to know at all times. So we need to understand all those things we learned in pre-calc about asymptotes and about holes in the graph and discontinuities, and all of that helps us with answering these questions. Okay, so now let's look at a piecewise function and see what we would do here. So now we want to find the limit as x approaches 1. Well, we learned before for the limit to exist, then the limit from the right and the left must be the same. So I'm going to do the limit as x approaches 1 from the right of g of x. Well, which function am I on if I'm to the right of 1? Well, x is greater than 1, so that's to the right of 1. So I'm going to plug 1 into that part of it. That's 1 cubed plus 1, which is 2. Okay, so that's what I get on that side. Now I'm going to do the limit as x approaches 1 from the left of g of x. So if I'm on the left, that means I'm on the bottom one. So again, I plug in 1, I get 1 plus 1, which is 2. Well, both of those things together then, that means that the limit as x approaches 1 of g of x is in fact 2, because the left limit and the right limit equal to each other. Okay, so therefore those limits are the same because those two limits are equal. We could even write that as an expression as we go from the right. It equals the limit from the left. Okay, and since they are the same, then that is the answer for the limit. So that's how that's going to work. So let's do this piecewise function. We're going to approach 2. And so we have to check from the left and from the right. So the limit as x approaches 2 from the right, again, watch your writing. X approaches 2 from the right, stays under the LIM. It doesn't stretch across the whole problem. H of x in line with the LIM. And we want to do this limit from the right. So when we're on the right side, then we're on the bottom expression because that's x greater than 2. So this will be negative 2 squared plus 4 times 2 minus 1. So that's going to be negative 4 because the negative is outside. So you do 2 squared and then take the opposite. So that's negative 4 plus 8, which is 4 minus 1, which is 3. Then we're going to do the limit as x approaches 2 from the left. Well, if I'm on the left, it means I'm in the other one. So I do 1 squared minus 4 times 1 plus 7. So I get 1 minus 4 is negative 3 plus 7. Or, yes, 1 minus... Oh, sorry. No, I'm not putting 1 in. I'm putting 2 in. I don't know where I got 1 from. I'm doing 2. This last problem was 1. So this will be 2 squared, minus 4 times 2 plus 7. I don't know where I got the 1 from, but we're doing 2. We're approaching 2 from the left. So I get 8 minus, I get 4 minus 8, so I get negative 4 plus 7, which is 3. And so, therefore, the limit as x approaches 2 of h of x is in fact 3, because the left and right are the same. If they were not the same, then we would say the limit does not exist. Okay? All right, so let's just figure out kind of what we need to do here. So, and I think this problem is different than what your thing says. So let me go back. I don't know why this problem is not the same, but that's not what I have on the paper. So I think you're supposed to have this problem. And so again, factoring is important here. So if you have trouble factoring, you need to work on that. You do not have time to be doing factoring by grouping and all that kind of garbage. You just need factors of -8 that add to 7. We have no choice but the first to be 2x and x. And then we know our outside term and our inside products have to be the -8 and 7. So that makes this have to be -4, because there's my -8. And that makes this, oh, wait, factors of -8, plus 1, -8 and 1, sorry. So we have, +8 and -1. Oh my goodness. Try that again. So I need factors of -8 that add to 7. That would be +8 and -1. So I need 2 times 4 to be +8, and then my other one is my -1. So there's my factors, and then the bottom factor's a little easier because A is 1. Factors of -20 that add to minus x would be -5 and +4 that add to -1. So again, I would have, if I plug in -4, I'm going to get 0 over 0. Clearly, this is 0, that's 0. But because it's limits, I can cross it off, and then I can just plug into what's left. Because again, the limits are equal. The functions are not exactly the same, but the limits are exactly the same. So now I get 2 times -4, which is -8 plus 1, or minus 1, which is -9. And then -4 minus 5 is -9. So my overall answer is 1 there. Okay, I'm going to do B quickly. I do not stress knowing the formula for factoring cubics. So I'm just going to tell you what you get. I usually keep that listed. I actually usually write that on the I have a formula for that written down. You are not going to need to know that formula. So really, I just want you to be able to use it if it's given to you. Okay, so that formula you can find, and then that's what would happen if you factored it. Those would cancel. Now I plug in 3, do your arithmetic, you get 27 over 7. Okay, and then I don't know why we have a C, so we're going to skip that one. All right, so now let's talk about simplifying complex fractions. So if I plug 0 in here, I'm going to get obviously 0 on the top, and then the bottom is going to be 1/4 plus or minus 1/4, so I'm going to get 0 over 0, and I need to simplify it. Well, this method for simplifying complex fractions is super important anyway. Like, you need to know how to do this. This is how you should simplify any complex fractions that you have. Complex means that you have a fractions inside fractions. You're always going to find the least common denominator of the little denominators, okay? So in this case, it would be 4 times x minus 4. And then you're going to multiply top and bottom by 4 times x minus 4. Then I'm going to show you how we're going to write it different to save a little bit. So basically, I'm multiplying the top and bottom by that. Well, what that actually ends up doing is this, and this is what I want you to normally do. So you're just going to multiply. Here was the original problem. I'm going to spread it out a little bit. What I'm going to do is I'm going to multiply every term, because if you multiply the top and bottom, you're going to distribute, right? You're going to distribute this. So I'm just going to go ahead and distribute it from the beginning. So I'm just going to multiply every term times 4 times x minus 4, because that's what you're going to end up doing. Now be careful, because I wrote that below. It looks like I'm multiplying on the bottom. That's kind of a bad way to write that. You of course multiply on the top. It's in the top. So normally I just go straight to this step. I find the least common denominator and then multiply every single term by it. The reason we do that is that this is why the least common denominator works, because we made it of factors of the little denominators. Well, now all those little denominators are gone, so that makes life much easier. Now the problem, and I'm not going to multiply it out, I'm just going to leave it like this. Don't multiply stuff out until you see what you need to do with it. The bottom will be x minus 4 from here, and then plus, and then just a 4. So then these will cancel out. And so then you're going to end up with your x on the top and x on the bottom will cancel. So you'll have 4 times x minus 4 is all that's going to be left here, which makes life much easier. And again, don't distribute because it's easier to plug in here. 0 minus 4 is negative 4 times 4. We get negative 16. So that's just the way that we can handle that. So let's do that one more time. So again, I have fractions inside fractions, and so I'm going to choose to multiply every term by the least common denominator. So the least common denominator is 2 times 2 plus x. So every term gets multiplied times 2 plus x. And of course, you're multiplying in tops when you multiply on fractions. Then you can go through and decide, then you divide out your common factors because now you're multiplying, and then that's going to leave you with the limit of, in the first term you have a 2, then you have minus parentheses 2 plus x. Don't mess that up, you want to distribute that. And then again in the bottom, don't multiply that out. In the top, if you distribute, you're going to have 2 minus x. The bottom is 2x times 2 plus x. Now 2 minus 2 will cancel. You'll have, becomes a 0. You'll have minus x over 2x times 2 plus x. But then now your x's can cancel. So now you just have minus 1, don't forget that's not just nothing, it's minus 1, and then 2 times 2 plus x. Again, don't multiply it out, easier just to leave it. Then I plug in 0 here, and so I'm just going to get negative 1 over 4. Okay, now I went through some of those kind of quickly, but this is a video, so you can always stop it and do that. All right, so we're going to do one more example, and then the rest of it is going to get left for doing in class. So the next thing we're going to do is talk about what to do if we're going to, what's called rationalizing the numerator, and that's when you have this big square root in there. And this method actually is a pretty decent method even later, and so therefore we're just going to go ahead and do it. And so we're going to talk about what to do. So basically what we do is the first thing we do on every limit is we would plug negative 1 in. But if we plug in negative 1, we're going to get square root of negative 1 plus 2, which is square root of 1, which is 1. So 1 minus 1 on the top is 0. Negative 1 plus 1 on the bottom is 0. So I get 0 over 0. Now I can't factor this one. It's not rational. So what we're going to do is we're going to use a technique which is called multiplying. We're going to rationalize the numerator. So we're going to multiply the numerator and the denominator by the conjugate of the top term that has this radical in it. The conjugate is to change that sign to the other one. And the reason that works is because we now have a difference of squares on the top. So the top part is now, you are doing, you basically, if you FOIL this out, multiply it, you're going to have first times first, which is going to be x plus 2, because you have square root of x plus 2 times square root of x plus 2. Your outside and inside are both going to just be opposites. That's why the difference of squares works. And then your last term is negative 1 times 1, which is 1. The bottom, again, do not ever multiply that out. Leave it, leave it, leave it. I can't stress that enough. Never, ever multiply out a denominator. Okay, super rare that that's ever going to be helpful. Occasionally with a random trig function, that's helpful, but most of the time it's not helpful. So never multiply out your denominator, never. Top is x plus 1. Bottom is x plus 1 times this square root thing that we made. And guess what? This is why we don't multiply out the bottom, because look what happened. Now you have factors in common that can cancel. Now, before you think the top just disappeared, it didn't disappear. X plus 1 over x plus 1 is 1. So there is a 1 in the top. Then this is your bottom. Now plug in -1, and now I get an answer. So I plug -1 in here. -1 plus 2 is 1. Square root of 1 is 1. So you have 1 over 2. Okay? So, and that's a very big method that we would use. Okay? So that's all I'm going to do on this video. The rest of it we can do in class, which will be like kind of combining all the methods and picking all of that out.